So we talked about the solubility of ionic compounds and about how things dissolve. Now we're going to look at some chemical reactions. And one of these, well actually there's two here, but one type is what happens when you get soap scum and other hard water deposits on the bathroom fixtures. So hard water contains dissolved ions. The harder the water, the more ions there are. And calcium and magnesium are the ones that typically cause the most problems. They form this gray curd or soap scum or bathtub ring around the bathtub. And that's because of their reaction with the components of soap. So laundry detergents are formulated to avoid this. They contain sodium carbonate. Sodium carbonate precipitates the calcium and the magnesium. Calcium carbonate, magnesium carbonate are not soluble to a significant extent. And so by adding carbonate to the wash in the form of the detergent, it gets rid of all the calcium and the magnesium. Because this gray curd stuff is what gets your white clothes all dingy. It's not that you weren't washing them enough or something. It's just that there's calcium and magnesium and it gums everything up. So we can write equations like this where we've got the calcium ion that's aqueous, and that will interact with a carbonate ion, and it'll form a solid compound. That solid compound then will precipitate, and we've done a couple of reactions where we saw precipitation. You mix two clear solutions, and then it looks like snow forming. Right? So you don't see snow falling in your washing machine because there's not that much calcium. But this little bit of calcium and magnesium precipitates out and then it won't stick to your clothing. So precipitation reactions in general are reactions where a solid, which is called a precipitate, forms when we mix two solutions. So a solid forms that was not there before. Here we have an illustration of a precipitation reaction. Potassium iodide, and if we think about our solubility table, potassium compounds are always soluble. Lead-2 nitrate compounds are always soluble. So these are both soluble. When we mix these together, we see this orange cloud form. We can't see through this. It's cloudy because the particles there are larger. And so that's what tells us a solid is forming. If we wait, that yellow solid will fall to the bottom and we could decant the liquid at the top. So this is going to form lead iodide, which is insoluble. Iodide compounds are typically soluble, but lead-2 is an exception. And then the other product is potassium nitrate, which is soluble, and so those ions just remain in solution. So we can look at the pictures here. So we're starting out with potassium ions and iodide ions, and they're separated in the water, and we've got lead-2 ions and nitrate ions, and they're separated in the water. And when we mix these two together, the lead and the iodide ions stick together, they form a solid, and the nitrate and the potassium ions are left hanging around. So I have a weird analogy for this. I've told you I think of the metals as masculine. So metals are guys and non-metals are girls. And so here we have this flask here is a party. And so potassium and iodide are going to this party. And they like each other okay, but they're not like stuck on each other, right? They're just friends. And here's lead and nitrate, and they're going to go to this party together, and they're just friends too, but you don't want to go alone. So at the party, lead meets iodide, and it's chemistry. It's love at first sight, right? These guys are just drawn to each other. And so this is that couple that is not mingling at the party anymore. They're on the back porch on the couch out there necking the whole time. They're making out. They are not really part of the party anymore. They separated out and they're stuck to each other. Okay, why do lead and iodide do that? Why do Joe and Sally do that and not Joe and somebody else? Right? It's kind of random seeming. We have those solubility rules to predict who's going to do that and who isn't. So we need to be able to predict what's going to happen and what the products are in precipitation reactions. And the way we do this is we look at the original compounds. So here we've got lead and iodide. They came in together. And we've got, I'm sorry, that's not lead, that's potassium. Potassium and iodide. And then lead and nitrate came in together. And what we're going to do is we're going to swap partners at this party and see if anybody precipitates, if there's any chemistry going on here, okay? So we'll see how potassium and nitrate interact. They're like, hey, hi, how are you? You know, just, they don't hate each other, but they're not really stuck on each other either. But lead and iodide will form a solid, okay? So these are ionic charges. And so we don't have a possibility of lead and potassium getting together because they're both positive charges and positive electrical charges repel each other. We can't have the negative ions getting together because negative charges repel each other. The only two possibilities are cation and anion. Potassium will not precipitate with iodide. If it did, it would not have come in as an aqueous solution, right? And lead does not precipitate with nitrate. It would have done that over here. So our possible products here are potassium nitrate and lead iodide. And we write these formulas based on what we learned in chapter 3. We look at the charges on the ions, put them together in the lowest ratio that gives you a neutral compound. And then you identify which, if any, is a solid by going through those solubility rules. You can mix two aqueous solutions and not have a precipitation reaction. Just like you can have a party where a whole bunch of people mix and mingle and nobody hits it off. No couples are formed, right? So precipitations do not always occur. Only when you get insoluble compounds do you get precipitates. So this example is potassium iodide and sodium chloride. You mix those together, there's no reaction. There is a physical change because now those ions are mixed together, but it is not a chemical change. It's not a chemical reaction. So we could write a chemical equation for this, but it describes something that isn't happening. And so we'll typically say, you know, potassium iodide plus sodium chloride, no reaction. And we sometimes even get lazy with that and write NR, no reaction. Oops. Okay, so here's the steps for writing equations for precipitation reactions. You got to start with the formulas for the two reactants, and you need to look at the formulas of the products that could form. So what I like to do is to write the ions with their charges below the reactants, swap the partners, write the new products, and then you have to refer to the solubility rules to identify if any of those possible products are insoluble. If all of them are soluble, no reaction. That's kind of what we always hope for because it's less work writing the equation. But if anything is insoluble, and occasionally you'll get both of them being insoluble, then you have to write the formulas for all the products. You have to indicate which is the solid, which one's aqueous, and you need to balance the equation. So we'll do some practice examples here. So write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. Now these examples are written to give us a little practice in nomenclature on an exam. I'll test you on the nomenclature separately from the precipitation reactions. But we have to write the formulas for these compounds. So ammonium is an ion, right? So we've got two ionic compounds here. So I'm going to write the equation up here, but in order to know the formula for ammonium chloride, I have to look at the ions first. So ammonium is NH4+ because you memorize it. And chlorine has a -1 charge because it's in group 7. So I look at those two, their charges are opposite and equal, and I can just put one of each, NH4, Cl. Is that aqueous? Is it soluble? Think about that list. On the first line, ammonium. Ammonium, lithium, sodium, potassium, always soluble. So this is ammonium, it's soluble. The reactants are always soluble. And then we've got iron 3 nitrate. So iron is Fe, IR is something else. And the Roman numeral tells me the charge, not how many there are. The charge on this is 3+. And then nitrate, I know 3- because I memorized it. To get a neutral compound from these guys, I need 1 iron and 3 nitrates. The second line of the solubility table says that nitrate compounds are always soluble, no exceptions. This one's also aqueous. Everybody okay so far? Now I'm going to swap the partners and see if anybody hits it off, right? So ammonium came in with chloride. I'm going to see how he does with nitrate. And iron came with nitrate. I'm going to see how he and chloride get along. So over on the product side, I'm going to write the new combinations. Now we always write the cation first and the anion second, like you address an envelope Mr. and Mrs., just because it's convention. It doesn't matter which pair you put first, though, because this is like adding, right? 1 + 2 is 3, and 2 + 1, also 3. The order doesn't matter. So I typically just take this first one and put it first for no reason other than just because. So I'm going to try those 2 ions together, and I'm going to try iron 3 and chloride together. Now, at this point, you kind of have 2 choices. You can go ahead and write, bless you, you can go ahead and write the products and then figure out if they're soluble or not. Or you can look at the combinations before you write the product formulas to determine if they're soluble. So this ammonium, this is going to be ammonium nitrate. Is ammonium insoluble with anything? No, the list says that ammonium is always soluble, right? So ammonium and nitrate are soluble together. How about iron and chloride? Well, chloride compounds are generally soluble, except with silver, mercury, and lead. Iron isn't one of them. So is this soluble or insoluble? It's soluble. Both of these compounds are soluble. So then this is an R, no reaction. Physical mixing, physical change, but no chemical reaction. Any questions? Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide mix. So again, I'm going to write the ion formulas to help me write the compound formulas. So sodium is Na+, hydroxide is OH-. And I put those together, I get NaOH, and that is soluble, aqueous. And then copper 2 bromide, Cu2+. The 2 is the Roman numeral 2 is the charge, and bromide is Br-. And so I need 1 copper and 2 bromides. And that one is also soluble. Bromide compounds are soluble except for silver, mercury, lead, and this isn't one of the exceptions. it's almost never going to happen where one of the reactants is solid. So now what I want to do is I want to swap partners. These two couples came to the party and they're friends and all, but we're going to see if anybody, gets into a real relationship. So we'll see how sodium and bromide get along, and how copper 2 and hydroxide. Well, sodium bromide, soluble or insoluble? Soluble. Sodium compounds are always soluble. What about copper hydroxide? Well, hydroxide is in the lower part of the table. Hydroxide compounds are generally insoluble, except calcium, strontium, barium, and of course the guys up at the top. So copper 2 hydroxide is going to be a solid, right? So then we have to finish this. So NaBr aqueous. Copper 2 hydroxide, I need 1 copper and 2 hydroxide ions, and that's going to be a solid because it's insoluble. And then I have to balance the equation. These are usually relatively simple to balance because all the polyatomic ions are staying intact because they're just switching partners. So I've got 1 sodium and 1 sodium, 1 hydroxide. Over here I have 2 hydroxides. So I need to put a 2 in front of sodium hydroxide. That changed the sodiums. 2 sodiums. And so over here, I need a 2 so that I have 2 sodiums. I can't change the formulas. I can't make it Na2Br. It's real tempting sometimes. You can only put coefficients in front. Now I've got 1 copper and 1 copper and 2 bromides and 2 bromides. And there's the balanced precipitation reaction. Any questions? This is putting together several steps that we've learned previously. We need to know formulas for ions and their charges. We need to be able to put those ions together to make a neutral compound. And we need to be able to balance an equation.